Alrighty, guys, we've got a few minutes before the lecture time. Are there any questions?
Hi, Professor.
Hey.
Do you mind explaining at least one of the problems in the first part of our homework 8, please?
Which one do you want?
Can you explain the first one at least, please?
So problem 1.1?
Yeah. I just needed to see, because I did attempt it, but I wasn't sure if it was, I guess, legal the way I approached it.
I mean, so do you have an opinion about whether X1 is a martingale or not?
I concluded no.
Okay. And how did you do it?
So I just realized that if we have e to the bt minus 1/2 t, then that is a martingale. But in this case, we only have t, so I assumed it'd just be not a martingale, or a sub or super in this case.
Yeah. So that sounds good to me. So you would take t bigger than s, and you would look at e to the bt minus t given fs. And so what you're saying is that, well, let's use that if I have minus a half t here, I'm good. Right, and then we can put the other half outside. So
Wouldn't one be positive to cancel? Or am I wrong?
we have minus t here, right?
Right.
So we have minus a half.
Oh, okay. I see it. My apologies. Yeah.
Yeah, it's okay.
I see it.
So the first term here is now a martingale, so this will be bs minus 1/2 s, and then you have e to the minus 1/2 t.
Okay. I didn't split it this way, but I see what you're saying. Yes.
I mean, there are many, you don't have to do it like this, but this was trying to follow along what you were saying, like that you wanted to use that you knew this was a martingale. Right, so that's not, this here is not the same as x1 of s.
Right. Okay. Thank you very much.
Yep.
So even though we weren't given the fact that t is greater than s, can we use that technique to solve the others? Because I was having trouble setting, I guess, the ones involving the Ito integral.
Yeah.
Can we assume, like you just said t greater than s while the problem didn't give it?
I mean, there's no s in the problem.
Right.
But this is, so if you want something to be a martingale,
You have to have something of the sort.
yeah.
All right. Okay. Because I thought the form I was supposed to obtain is e to the bs minus s for it to be a martingale.
Yes.
And then we were given just t is in the interval 0 to 1. So I didn't know how to proceed from there. And in our notes, we didn't really explain this technique.
Well, I mean, if you look up, you flip through over to where it says martingale. Right, martingale, page 74.
Okay.
And then let's see what he says. So you take in this case t bigger than s, and you say mt given fs has to be ms.
Okay.
For all s less than t.
Okay. So for 2, for instance, I set it up as in I placed what was given to us, and then I condition it on fs, and then I use the same technique. Would that work for problem 2?
It would.
Okay, okay, I got it now. Thank you.
Okay. let's get started on tonight's lecture. Right. So what we've been doing is we've been trying to get the E2 integral defined. Right, so we started out with the simple processes. So we had the integral from say 0 to t of delta u n db. So say that you had a sequence of simple processes. Then we know how these guys are defined. This here is this is defined as a sum. Say that t is in between some tm and tm plus 1. Then you would be summing here from delta t say k btk plus 1 minus btk. And then you're summing from S0 up to n minus 1. And then there probably is a little bit more. There'll always be this this little piece of delta t, and then it'll be tm, and then it'll have bt minus btm plus 1. So that's how we do it for the simple processes. This is how the stochastic integral is defined for one of those. Just one thing to note is if this guy is non-random, right? So it could, for example, be so there's no omega dependence. And just to note that this quantity here will then be normally distributed. Then you have the integral from 0 to t of delta u n dbu. Well, this is going to be normally distributed. It means 0 because it's a Martingale expectation 0. And then the variance we use isothermometry. So that was delta squared du. So if you have a non-random integrand, you're going to get this. And then we passed on to a limit. Then we took a limit. We take a limit as n goes to infinity. And then we're going to get this integral from 0 to t of delta u dbu. This is going to be defined as some limit of these where there's a connection between the two of them, and the connection is that delta u minus delta u n, when I square and I integrate, this thing goes to 0 as n goes to infinity. So we talked about this. One other thing we talked about last time was we actually computed. We did an example where delta u would be bu. Actually, this is not simple, but we did it nevertheless, and we proved that the integral from 0 to t of bu dbu, this would actually be 1/2 bt squared minus t. Right, and so this is just another note. This is not normal. This integral here, this is not normal. There are many ways to see that, but for example, 1/2 bt squared minus t is lower bounded. This is bigger than or equal to minus 1/2 times t. Right, and a normally distributed random variable is not lower bounded, right? It can take any real value. A normally distributed random variable would take values anywhere on the real line, and in particular, it cannot be bounded from below. So this result, this note we had out here, it doesn't work when the integrand is stochastic, like the Brownian motion. I should also say here that the properties we know, or we proved for simple processes, they carry over to the general case. So one of them we saw was the stochastic integral. One of the most prominent features is that this is a martingale. We proved that the correct variation of the time t, this is going to be the integral from 0 to t. So the way to write this, there's no t that goes inside here. So what people often write is a 0 here and you put a dot up there. The correct variation of the stochastic integral can be computed as a Riemann integral. We did that one. We also proved the e to the isometry. So if I take the integral from 0 to t and I square the integral, then the e to the isometry says that, well, I can do this by integrating from 0 to t of delta u squared du. Or if you want this one here, you can pull it inside and take the expectation of delta u squared du. Okay. These are some of the things that we had talked about. We've actually proved these properties here when delta was simple. So they carry over to the limiting case. Where we ended up last time was Ito's lemma. So the last thing we did was Ito's lemma. So Ito's lemma says you take a function from R to R. It has to be C2. Right, so it has two derivatives that are continuous. Then Ito's lemma says f of bt, and then you can take t, for example, bigger than s. You write this as f of bs plus, and then this integral from s to t, f prime of bu dbu, and then the term that we always have to remember when we're dealing with stochastic integrals is the correct variation term from s to t, double prime, and then the correct variation of Brownian motion, which is du. So this is for functions that go from R to R and that have two derivatives. And very often, so there's there's a shorthand notation for this. Very often you'll see, instead of writing all this stuff out here with integrals, what you'll see is people write a d on the left-hand side. Then you write f of bt. And then on the right-hand side, you will drop the integrals. You write this as f prime of bt dbt plus, and then 1/2. You drop the integrals, f double prime of bt dt. This here is referred to as the dynamics of f of bt. There's no meaning by itself. It's just much shorter to write than all this stuff up here. There are some people that refer to call this here for the differential. I really don't like that expression. So some people will do it, but you will not hear me do that. I won't do that. For me, this will always be referred to as the dynamics of f of bt. Any questions on this?
Is there any relationship between this and the dynamics of wealth that we were doing?
Yes. Yes.
How so?
Well, we haven't talked about wealth in continuous time, but wealth dynamics. This is very much in this spirit here.
Okay.
You need to have a little bit of patience. We're working towards finance, but we're building up some of these tools from continuous time stochastic calculus. But in discrete time, what you would have here would be delta, and then you have delta of f of b n, right? So what would that be? It will be f prime of b, say maybe n minus 1, and then you have your delta b n here. You would have 1/2. You would have f double prime. Maybe it's b n minus 1, and then you have a delta. And so I'll call these things here for the dynamics in discrete time. But what you have over here on the right-hand side, this would be f of b n minus f of b n minus 1, right? So this here is going to become, when we apply it to our problem in pricing derivatives, this here is going to become the wealth dynamics. Other questions or comments? Ibrahim, you need to have a little bit more patience. It's going to take me a week to get there. But we're getting there.
Yes, if you could accelerate it, that'd be amazing.
But I can't. Yeah. We're trying.
I like the finance component.
Yeah, it'll be there. It'll be there. So what I want to do now is go through a number of examples for using Ito's lemma. We did one last time. We're going to do 3 today. Up here, you see that there's a function of just one variable. There are more general formulas of Ito's lemma. You can have a function of r and then also time. then that one needs to be C21. So there's going to be two derivatives with respect to the first one and one derivative with respect to the second one. And then you can look at the dynamics of f of bt and t. And there's going to be there'll be more components. Now this will be, instead of just having two terms, there'll also be a term with t here. So you get f, the derivative with respect to the first entry, f1 of bt t and dbt. You need two derivatives with respect to the one where you have Brownian motion. So this will be f2, this will be f1, bt t. And then the credit gradation, this is going to be dt. And then there'll be a new term because you also have a second entry in here, but this is just time. So it'll be f2, bt and t and dt. So that's how each assignment looks like for a function that is being applied both to a b and t. And of course, you could do even more general. You could have like a two Brownian motion setting maybe. So you could do a function that will go from say R2 to R. So now I'll need it to be both C2 and 2. So if I took two Brownian motions and I plot them in there, so I'll have df of bt and maybe wt. So I have two Brownian motions. So what would I get? Well, I'll get the usual terms. I'll get derivative with respect to the first entry, bt wt d bt plus, and then I'll have this guy, 1/2 f11 bt wt, then the credit gradation of that Brownian motion is dt. And then we also have to have derivative with respect to the second entry, so this will be f2 of bt wt, and then the other Brownian motion, 1/2 of f22, and then the Brownian motion w's credit gradation, this is still dt. And what else should we get? What other term should we get here? What other term could one imagine that would appear? Cross term, very good. How many cross terms, Raksha, do you expect? We'll probably get two. F12 and F21 coming in with a half. So we're just going to get one full one. F12. And then what should we integrate with respect to? I need to put d of something here. Well, it's going to be something about how b and w d work together. So I'll put in here the cross variation, where the cross variation between two Brownian motions is defined as the limit as, and then we'll be summing absolute value btn plus 1 minus btn times wtn plus 1 minus wtn. This is my cross variation. And so for Brownian motions, so very often I should here say always, our rounding motions B and W, we have a 0 cross variation. Right, so in that case, this cross term here, it's really not there. And we just left with the first 4 terms. Okay, so these are all variations of the same object. And of course, you could also have B, W, and then you could put a time component in here. And you're going to have more rounding motions than just 2. And every time you want to have a rounding motion, you need to have 2 derivatives. Every time you want to have a t, you need to have 1 derivative. So you can build it up like this. The examples we're going to be looking at are all going to fit into these versions that we have on these slides. So let's do some of them. And the first one we're going to do is so this is an example, and it's in the textbook. This is example 44448. This one here, this is famous. This is the geometric rounding motion. This here is really the stock price. So Ibrahim was asking about this. This is the stock price process in Black-Scholes. So this is in Black-Scholes world. This is the assumed stock price process. So geometric rounding motion, we use the same symbols as Steve does. Where's this with alpha and sigma? So he's going to say, well, let's look at ST. Let's look at ST being, well, it's going to be S0, and then it's going to be an exponential. You're going to have a sigma BT here. And then there's going to be minus 1/2 sigma squared. So this is the mathematical structure that was asked about in the very beginning. And then there's going to be an alpha. So here, S0, this is a positive constant. Sigma and alpha, the R and R. So this is the assumption. This is the assumption in Black-Scholes. That's how the stock price looks like. And for example, there are things to note here. Like, so just some notes. Just some notes. If I look at ST and then I divide over by S0, then I'm going to get an exponential, so I can take log here. If I do that, I'm going to get sigma BT minus 1/2 sigma squared T plus alpha T. Right, so I divide it over with S0. I took log. I'm going to get the stuff inside the exponential. This is going to be normally distributed. Let's see what the mean is. All the randomness is inside the rounding motion, so, and he has 0 mean, so the mean is going to be over here. It's going to be alpha minus 1/2 sigma squared times T, and then it's going to be sigma squared times T for the variance. So we have that thing. So the distribution in Black-Scholes is going to be log normal. So ST is log normal. If you apply log, you're going to get something that's normal. Another thing we could try to do is if I take T bigger than S, I could compute the conditional expectation of ST given Fs. So I'll plug in what is ST is. This was my S0. And then I have this E alpha t out there. And then I'll put in the conditional expectation, e to the sigma bt minus 1/2 sigma squared times t, given fs. But as we had talked about, what is inside here, this is now a martingale. This is now a martingale, and I'll get here, this is S0 e to the alpha t, e to the sigma bs minus 1/2 sigma squared s. And so we can start asking, like, how does this relate? How does this relate to SS? Well, we can see there are definitely some similarities, right? If I take SS, I've just put S's everywhere here. So sigma bs minus 1/2 sigma squared s plus alpha s. We have a lot of the same terms down here. So if I write this here as S, SS, this alpha t will have to be there. But then we're going to get a plus alpha s here, so I need to subtract that away. So it's not really a martingale unless alpha is equal to 0, but you can see, depending on the sign of alpha, so depending on alpha sign, we get ST is a super, ST is a super martingale, ST is a martingale, ST is a sub martingale. Let's see when we get what. Well, when alpha was equal to 0, I would get exactly SS, and this would be when alpha is equal to 0. Okay, so when alpha is positive, what do I get? Do I get a super or a super? Alpha positive, then this quantity here is bigger than 1. I'm going to get that the conditional expectation is going to be bigger than its current value. So that means it's a sub martingale. And then, of course, the super one is when it goes down. Any questions? Any questions before we start doing Ito's lemma? So it's screaming up here, and ST is a function of BT and T, right? So we can write this as a, we can plug that formula, that function, into Ito's formula. So if I look at, so to use Ito, we define the function. So what should we take for our function? So we should have f of x comma t. This should be, well, it'll be S0 e to the sigma x minus 1/2 sigma squared t plus alpha t. And then we need all the derivatives in order to use Ito's lemma. So we need f1 of x and t. It's an exponential, so we want to get f back. This will be f of xt times, then I need a sigma that's going to come down here. This is going to be my sigma. I need f11. Two derivatives with respect to the first entry. So I need the derivative of this guy here. This will give me f of xt sigma squared. And then finally, I need the derivative with respect to t, the second entry. Again, it's an exponential. It will give me the function again. And then I need to multiply onto the derivative of what's inside the exponential with respect to t. So I'll get alpha minus 1/2 sigma squared. Okay, so I just computed a bunch of derivatives, and then we can use each formula. Each produces the dynamics f of bt and t. So let's go through it again. Let's have a look. We have Brownian motion in the first entry, so this will give me f1 bt and t dbt. I have Brownian motion in the first entry. I always have to remember quadratic variation term. So this is 1/2 second derivative with respect to the first entry, and then the quadratic variation of Brownian motion. This is dt. And then finally, there's a t over here, so I also need a derivative there. This is going to be f2 btt dt. And now I plug in. Now I'll plug in. We will have f1. This is going to be f1. This is going to be right. This f of bt here is f of bt and t. This is my s. Right. So this thing here, this is dst. It's the stock price dynamics. And so what will I get is f1, this is going to be f, so that will be my st again, times sigma dbt, plus 1/2 f11, so this is again f, that's going to give me my st. And then the double derivative, that's sigma squared, and then dt. And then f2 is again f, so that's going to be my st, times, and then alpha minus 1/2 sigma squared dt. And we can see now that there's a minus 1/2 alpha squared, no, minus 1/2 sigma squared here, and there's a plus 1 here, so we can simplify a little bit. We can write this here as st sigma dbt plus alpha dt. So remember this dynamic form, so remember this is shorthand notation. This is shorthand notation for when you write out the integral. So let me write out the integral. St is equal to S0 plus, and then an integral from 0 to t of this stuff up here. So this will be Su sigma dbu plus an integral from 0 to t Su alpha du. And so again, we see that St satisfies an SDE, right? Because you have S here, you have S here, and you have S here. And so S appears both on the left-hand side and on the right-hand side. And so what kind of an object would satisfy such an equation? That's why it's called an SDE. We had them last time too. And here's another example. And well, it turns out that this object here, right, there's no S on the right-hand side here. There's just sigma, there's just B and T on the right-hand side. Turns out that this ST here satisfies this equation. So naturally, there are two terms here. And naturally, the first term, this is called the martingale term. This term, the dt, this is called the drift term. This is called drift. So we have martingale and drift. So sigma controls the martingale term, alpha controls the drift term. SDE, this is the stochastic differential equation. And it should, I mentioned this last time too, let me just mention it again, it should more appropriately be called not a stochastic differential equation, it should be called a stochastic integral. Because after all, we have integrals here, but nobody calls it that. Everybody calls it a stochastic differential equation. Other questions, comments? So in this example, we started out with the definition of the process in question. So ST was the starting point. Let's try to flip it around now, and let's, because I mean, I could have done exactly the same thing here. I could have started out giving you this equation, equivalently giving you this equation here, and asked the question, so what is S equal to? So let me flip it around and do another example. So this is the next one. 4, what will it be, 10? This one here, this is called, the other one is called geometric bounding motion. This one here is called an Ornstein Uhlenbeck process. So people just call it OU. In math finance or in quant finance, this is used to, this is the standard, model for stochastic interest rates. For those of you that will end up on a disk working with fixed income instruments, there will be a model. There'll be a model for stochastic interest rates, and I guarantee you this here is going to be the one that you'll be working with. The name is called Vasicek. Just like the other one was called Black-Scholes, this one here is Vasicek's model. And this is the completely dominant model for stochastic interest rates. So here, the tables are turned a little bit. You start out with this equation, not this one, but something like this. And then you're trying to figure out what should actually be the solution. Right? So you start out here with DRT, the form. You start out with the SDE. This is, so R is going to appear on the right hand side. This is alpha minus beta RT dt plus sigma, and then Brownian motion, and we call it dBT. Like where alpha, beta, and sigma are constants. So that's the starting point. So we want to know now, we want to know things like, can we solve it? So can we solve? So what's the solution? We want to know something about like what's the distribution? What's the solutions distribution? Basically, what we want to do is we want to answer exactly the same questions as what we had before. We want to have exactly the same. So we want to, what is the formula for R here? This formula here works for the geometric bounding motion case. What is the formula here for this case? And so this is now a lot harder, because how do we get started on something like this? well, maybe if you recall, you've probably seen an ODE somewhere. So if you looked at linear ODEs, so there's no Brownian motion in an ODE. So you would look at, what could we have here? We could have a D, so dRT would be alpha minus beta RT dt, and so maybe what we can do is we could divide over by dt, so that dRT over dt, that would be alpha minus beta RT. So this looks like what? Right, so this is the same as saying that R prime of t would be alpha minus beta RT. What kind of an R would we be looking for here? What kind of a function am I looking at here? It'll be something that has a derivative, which is a constant, minus another constant times the function itself, right? So if alpha is not there, it's something with an exponential, because you have the derivative of a function is equal to something times the function itself. It smells like an exponential. How do we figure it out? Well, if I look at R of t tilde, what should we do here? Get rid of this term over here. This is something with an exponential, so maybe it's an e to beta t times rt. So we're looking at this here. We're just doing a little recap on linear ODEs. So maybe if I looked at this function here and try to compute the derivative, what is the derivative of this guy, right? So what is, if I take the derivative with respect to t, take the derivative with respect to t, what would I get? Well, it's a product, so we'll use the product rule. We get this would be e beta t times something. The derivative of the exponential function, this is going to give me beta times rt. And then I need to take the derivative of r, so that would be r prime of t. And then I can use what rt is. This here will become e to the beta t, and then it'll just be an alpha there now. Because r prime had this form, take this form, plug it into this bigger form here. So then I have a derivative, and now there's no r, right? There's no r. There's no r on the right-hand side. So then I should be in good shape, because if I then just integrate, I can just integrate, so I'll get r tilde t would be the initial value, r tilde 0, and then an integral of r tilde prime of u du. R tilde 0, well, if I take tilde 0, the exponential function is just a 1, I'll just get r 0. And then on the right-hand side, what would be r tilde prime? That's the thing we just computed. This was alpha e beta u du. But that's something I can compute. I can figure out what this is. I figure out what this is. This is r0 plus, and then it's alpha. I need to integrate the exponential function. This is, I need to divide by beta, and then e beta u, u being 0, u being t. This is r0 plus alpha over beta, e beta t minus 1. Right, so I'm not doing anything fancy here. Now let me replace what r tilde t is. That was this expression up here. So RT is equal to, I'll move this to the other side, e to the minus beta t r tilde t, e to the minus beta t, and then what was r tilde t? This was this stuff up here. This was r0 plus alpha over beta, e to the beta t minus 1. So I arrive at an expression that this function here apparently solves the ODE here. This thing solves that r prime of t is equal to alpha minus beta RT. I'm hoping some of you have seen linear ODEs before. We talked a little bit about them, not much, but we talked a little bit about them. But this trick here, multiplying onto this exponential factor, this is quite useful. And so this gives you a flavor of, if I wanted to solve an equation that is linear, there's no randomness here, right? These are just linear ODEs. There's no randomness. There's no randomness here. It's just calculus problem related to ODEs. I come at this solution here. So what should we do in? So now in our case, so back to our case, back to the OU process. It had the form dRT. What was it we had written? This was alpha minus beta RT dt plus that sigma dBt. How do we solve this guy? Well, we could try to mimic what we did before. It worked well introducing this R tilde. Maybe we can do the same thing again. So let's try to do RT tilde. Try to do RT tilde. This would be e to the. This would be e to the. What was it? We had beta t, and then RT. And so the next step we did in the linear case was, if we had him, we would now compute the dynamics. Okay, so let's compute the dynamics. Here we have something with t, here we have something with r. Let's compute the dynamics of r tilde t. Well, it'll be very similar to before. It'll be e beta t, and then the beta comes down. We'll get rt dt, and then we'll have plus drt. And then we'll plug in what drt is. And as before, we can see that the Brownian and that the beta times r will disappear. You can see as before that the beta r term will cancel out this beta r term here, and we'll be left with e to the beta t, and then what will survive will be this alpha dt plus sigma dBt. So that is quite similar to the calculation we had before. Before, the only thing that survived was the alpha. Now the thing that survives is the alpha as well as the sigma. But again, there's no r term. There's no r terms. So we integrate. We'll integrate and we'll get that r tilde t is equal to the initial value, an interval from 0 to t, d DRU. We'll plug in what DRU is, 0 to t, and this would be e to the beta u alpha du plus sigma dbu. So this will be, again, we'll again get the Riemann integral and the Brownian integral sitting next to each other. We get r tilde 0, this will just be r0. And then we'll have the first integral, this would be alpha over beta times, what was it we got last time? Beta t minus 1 plus, and then you had sigma, integral from 0 to t, e to beta u dbu. So what we note at this point is these terms here, there's no randomness. We just have a constant, the initial value. Then we have these alpha and beta. There's a time-dependent function here, the exponential function. Over here, we have randomness because we integrate in respect to random motion. We have a constant, and we have a deterministic function. So this thing here is going to be normally distributed because there's no randomness in the integrand. This thing here is not random. So that was one of the properties we had early on. We have a stochastic integral. The integrand is not random. We're going to get a normally distributed quantity. The mean is 0, and the variance is sigma squared. And then the integral from 0 to t, and then this guy squared, e to the 2 beta u du. So we are itching closer. We now know that r tilde t is normal because it's a constant plus something that is normally distributed. And as before, if I know what r tilde is, I can simply just solve here for r. I can get that rt is equal to r tilde t, and then move the exponential function to the other side, e to the minus beta t. And so I take this expression, plug it in here, I get e to the minus beta t, and then r0 plus alpha over beta, e to the beta t minus 1 plus that stochastic integral. And so this is again going to be normally distributed, simply because this is a constant times a normally distributed random variable. That's again going to be normally distributed. And we can see this here is our solution because RT is here and there's no RT on the right hand side. Right, so we're claiming that this one here has dynamics, dRT being alpha minus beta r dt plus sigma dbt. Are there any questions on the Ornstein-Uhlenbeck process?
Can you explain how you found out that it's normal 0 sigma squared and the integral?
Yeah, I can do that. Right. So how to see normality. Right. If delta is simple and non-random, then I'll very often not write it like this, but I'll write it like this. Then the stochastic integral we have a formula for it. This was this, maybe I can integrate here up to like a Tn, then this would be delta at some tks times b tk plus 1 minus b tk, and then an integral, so that would be a sum from k equals 0 to, say, n minus 1. Right, in this quantity here, this is going to be normal with mean 0, and then the variance is being tk plus 1 minus tk. That was the definition of the stochastic integral. So then I can go one out. And now I'll use that this is non-random. So if I take a normally distributed random variable, multiply it onto a constant, I'll again have that this thing is normally distributed. The mean is not going to change, but the variance is going to change. I'll have delta tk, squared times tk plus 1 minus tk. And then I'm summing them. And the all independent, right? This increment is independent of all the other increments, so I'm going to get that the overall quantity here is going to be, I'll just have to add up the variances. Are you good so far, Ibrahim?
Yes, I follow now.
Okay.
Thank you.
But this is only for when it's simple. Like our case is the one where delta u is equal to, what was the thing? It was this exponential function. Right, and this is not simple. So then you have to approximate. So again, you need to approximate. You need to approximate. So you write this delta, these simple ones, you have to write this as what would be probably a to the beta t k for u between tk and tk plus 1. And there's an n on these t's. So now these are simple. You can use the result and then pass to a limit. So you could do something like, for example, if you were to look at a moment generating function, e to the t, and then this integral, or I shouldn't use t here, maybe I should use a, an integral from 0 to t, delta, this function up here, e beta u, dbu. Well, the first thing you would do is you would write this as an expectation of E and then A, and then you have this limit up here of these delta n u dvus. So you have to pull the limit outside. And this is one reason why I really don't like this moment generating function. I would much prefer if you could use the characteristic function, because then in absolute value is going to be bounded by 1. And so we can now pull this limit outside. You can pull this limit outside as n goes to infinity. E, I, A, and then this integral. Well, now we know exactly what that is, because we have that this is given up here. This thing here is the limit, and then you have E, and then the characteristic function for the Gaussian is minus 1/2 a squared, and then the variance of this thing, this was the integral from 0 to t delta u n squared du. And then you pass the limit back inside, and you're going to get that this is minus 1/2 a squared integral from 0 to t e to the bu squared du. And then you finally have it that this really indeed is Gaussian. Ibrahim, did that make sense to you?
It did. I'm just going to review more. Thank you.
Are there other questions about the Vasicek model, the Ornstein-Uhlenbeck process? The last example we have is 411. And then we spend the last 10 minutes of class, 15 minutes of class doing that. This one here is more tricky. This one here is called the Feller process. A lot of people call it for a CIR and a square root. This is with an E, Feller with an E, Feller process. So here the SDE, it looks a lot like the Ornstein-Uhlenbeck process, but not quite. Where is the Ornstein-Uhlenbeck process? We need running motion. Here we go. But this here is the Ornstein-Uhlenbeck process. So it's a linear drift, and then there's a constant volatility. So for the square root process, as the name indicates, there's going to be a square root somewhere. And the Feller process has this form. It's very similar to the Ornstein-Uhlenbeck process, but there is one key difference. The drift is the same, and the volatility has a sigma, and then comes the square root. There's a square root of RT here. Right, so this is a main difference to Ornstein-Uhlenbeck. And so what you can see is, so just to get some intuition, say that R0 is positive. So the process starts out somewhere up here. And then it moves around. And if it at some point hits 0, it moves around and at some point it hits 0, then what happens? Well, now R is equal to 0. So this term is gone. R is equal to 0, so this term is gone. So then if you want it to stay positive, what we need is just to give it a little push back up. Then the change in R is going to be alpha dt. So then it's going to pop back up and keep moving. And you can see if if alpha is positive, RT is always positive. And this is not so this is going to imply that there's just no way RT cannot be normal. That's impossible because it's a non-negative random variable. It's again an SDE. So unfortunately, this time there's no known closed form solution to the SDE. So I'm not able to write down RT in this explicit form, or in some explicit form, as what we had before. Like in the Olmsted-Uhlenbeck case, we had a very explicit form here. RT was given by this long formula. That's not the case. That's not the case. You can't. There's no such expression in this case when you have a square root here. At least not that that we know of. So we can't do that, but maybe there are other things we can do. We could, for example, try to apply the same trick as before. So we could apply the same trick. Right, so we look at RT tilde, which would be RT, and then times this e to the beta t. And so what would we will get here would be dRt tilde. This would be, we have this beta out there. And then we get beta RT dt plus dRt, exactly as before. Exactly as before. So we will have, we'll plug in for dr here, we'll plug in this long formula. And we'll be ending up with, very similar to before, it will be that alpha RT dt plus, and then there'll be no alpha. It'll be an alpha dt plus the sigma square root of RT dBt. So this doesn't look nearly as nice as before because there's still R dependence. But maybe it's not so bad. One thing we can do is we can switch over and write out in the integral form. So we'll have that RT tilde, write it out the long way. This would be R, say tilde. We'll have an S here. And then we'll have an integral from S to T. And then we write out the first integral will be dt, e beta u du. And then the second term, integral from S to T. We have my e beta u sigma square root of RU dBu. And so it's again not as nice as before because there's this square root sitting here. And in the Olmsted-Uhlenbeck case, we didn't have to deal with that. Like in the Olmsted-Uhlenbeck case, there was no square root here. Well, we do know that this object over here, this is a martingale, right? Because it's a stochastic integral. So for example, I will get from here that if I'm looking at computing the conditional expectation R tilde t given Fs, I can't say what that is. This would be RS tilde. Then this integral here, we had that before. This was alpha over beta, and then it would be e to the beta t minus e to the beta s. Plus the conditional expectation of the stochastic interval, but that's equal to 0 because of the martingale property. So we know what this here is. We could also try to, so if I take s to be equal to 0, so in particular, for s being 0, you have that the expectation of RT tilde would be, well, the initial value, alpha over beta, e to the beta t minus 1. And then what I could do is I could write this here as an expectation of RT e to the beta t. So I'll get the first moment of R should be e to the minus beta t R0 alpha over beta e to the beta t minus 1. So I might not get a solution to it, but at least I can get, for example, the first moment. Any questions on what we had on this slide here? So the best way to slow me down is to ask questions. If you feel like stuff is moving fast, you can slow me down by asking questions. Are there any questions on what we have here? So Ibrahim said in the beginning that he was quite interested in quantitative finance, and I agree. So in practice, so all companies, everybody uses OU to model interest rates. So what's going to happen here is that for us, the money market account, this is going to have the form DS0T, and this is going to be given by, it's going to have a set of dynamics, and you'll have this form here. So in practice, everybody uses this OU. So if you are to write down, the money market dynamic, so this, we can solve this SDE here. This is now an exponential. So we can write this here as, well, the initial value is 1. We will have an exponential of an integral from 0 to t of RU du. And this is a smooth function of t. I can take the derivative, and I can see that this derivative, right, if I take this one, I can take the derivative with respect to t. I'll get that dst0 dt. I can put d here and dt here. I'll get d here, dt here. I'll put d here, dt here. I'll get that the exponential derivative of the exponential will be itself is t0, and then times the derivative of the integral. This will be rt. And then we get back to exactly what we have up here. We move this dt over on the right hand side. And we're going to get we want to get these dynamics up. So in practice, everybody uses an OU to model interest rates RT. This is in practice. So in academia, there are two competing models. There are two competing models. It's OU and the CIR. It stands for Cox. Ingersoll and Ross, they have a model. And so here is OU and CIR. So this here is the square root. Right, and this one here was normal. So in practice, people are using a model for interest rates that allow for negative interest rates. This allows for a negative interest rates. And the CIR, well, this is the one that could be positive. This one here is non-negative. In practice, everybody uses the OU process. Nobody uses the CIR in academia. So when you read textbooks, you will find both of them being presented. And the same thing is true in our textbook. There's quite a bit of material on the CIR process for when it's applied to model interest rates. Okay, we are running out of time. Are there any questions before we call it a night?
Professor, do you know when you're going to release the practice problems or the set of problems for the final?
Yeah, I mean, it's up on the website. It's been up there for a long time.
Wait, for the second exam?
Yeah.
Oh, whoops.
Let me just show you. I mean, unless I messed up. I hope I put them up. That was at least my intention. This is where we add files. Maybe it's not. Maybe it's just all on my computer. But they have been available for a long time on my computer. I just apparently didn't upload them. Yeah, I have them right here. They're sitting right here. I'll put them up as soon as we're done with the lecture. Are there any other questions or comments? Okay, so for those of you that haven't signed up for the midterm, for the final, please do so. And for those of you, yeah, so if you haven't signed up, send me an email about the time slot that you want. And otherwise, I'll see you guys for office hours on Thursday and Friday mornings this week. And there'll of course be a lecture on Thursday night. And then I'll put these problems right up in emails. All right. Good night, guys.
Thank you, Professor.
You're welcome.